The choice of a reducing agent in a particular case depends on the thermodynamic factor. How far do you agree with this statement? Support your opinion with two examples. We fully agree with this statement. Obviously, thermodynamics is the key. If a reaction is not possible as per thermodynamics, it would not happen. Thermodynamics is the very fundamental basis or the basic criteria for deciding whether a reaction is feasible or not. What do we mean by that? The meaning is very simple. Say, just let us consider two very basic equations, and they are delta G is delta H minus T delta S, and delta G is also minus RT ln K. Now, if we know that some reaction has to happen, that means delta G has to be negative or delta S has to be positive for, this is delta S universe. Delta G is only for the system, delta S is for the entire universe. It has to be positive for a given reaction. If we can ensure this criteria is met, then we can say very well that a reaction would be feasible. Now we are talking with respect to metallurgy. We are saying the choice of a reducing agent in a particular case depends on thermodynamic factor. Yes. How far do we agree? We said, but I think we need to explain it more. This is actually summarized very efficiently in a diagram called AIIMS diagrams. What do AIIMS diagrams contain? AIIMS diagram contain graphs of delta G versus temperature for oxidation of various metals. Even non-metals, for example, carbon is also there, but then largely because metallurgy pertains to metals and we are mostly interested in metals, so we do plot all the metals along with the relevant non-metals. I'll give you some examples. Say for example, you are considering zinc. Now zinc can get oxidized giving you zinc oxide. Yes, very well. And if you consider, say, a second graph, and that would be the graph of carbon. C plus O2 gives you CO2, say for example. Now, with temperature, delta G values keep on changing, right? So, if we consider a temperature like this, say at around, say 600 degrees Celsius, what happens? You find that the position of zinc is lower in the graph as compared to carbon. Now, there are two possibilities. Can zinc reduce carbon dioxide to carbon, or can carbon reduce zinc oxide to zinc? Lower the position, more negative is delta G for formation of the relevant substance. If zinc is lower, like the red line, at this temperature, red line is lower than the purple line. What does that mean? That means zinc oxide is a stronger reducing agent to zinc cannot, ZnO cannot be reduced to zinc by carbon at this temperature. Okay, very interesting. And could there be any other metal? Yes, very much. Say, for example, at the same time, if you're talking about the graph of magnesium, this graph happens to be below zinc. So, at the same temperature, since magnesium lies below zinc, magnesium can reduce ZnO to Zn at this temperature. So these are two examples. At this 600 degrees Celsius temperature, magnesium cannot reduce zinc oxide to zinc, but carbon cannot reduce zinc oxide to zinc simply because of thermodynamic factor of delta G.